Yeah, those ones that look like this and are really weird and super repetitive. Yeah, I know exactly what you're talking about. Great. So yeah, as we've mentioned, there's sort of three really popular RAD pipelines, and we have developers of two of those on. And so I don't want this to be a battle of what RAD pipeline is best, but it would be interesting to hear a little bit about what are the relevant differences between these pipelines, especially for someone who's trying to choose like what pipeline should I use for my very first RAD-seq analysis. And so maybe if Jon and Isaac want to touch on that first, and I would also like to hear, especially from Melanie, since she's tested a few of these.
This is awkward.
Go for it, Jon. Yeah, no, go for it, Isaac.
I posted another link in the chat. I spent a little time doing kind of like a brain dump of all of the kind of prompts, and so I don't, we probably won't get to talk about all this stuff, but you can come back and look at this stuff later. And so here I kind of like, I want to less about the differences and more about the strengths of IPyRAD, just like the documentation is really good. And I know that, let me put it this way. It's been a while, but I've run experiments with like a horse race experiment with docent and IPyRAD and stacks. And they're all like within tolerances, they're all great. They all work really well. I mean, there's different kind of ways that the parameters can be tuned, but at the end of the day, they all can get you to where you're going. The last time I did this test, docent honestly was faster and as accurate or more accurate than IPyRAD with simulated data, but again, it's like, sorry, outside. But for the things about IPyRAD that I tell people, or that I appreciate myself when I'm using it, is the command line super easy to use, the params files like super easy to manipulate, the documentation is really good, it parallelizes super easily across compute nodes on high performance computing clusters. And the other thing that I'm super excited about that I really wish that people like knew more about, but I only have myself to blame for this because we haven't finished the publication yet, is the IPyRAD analysis tools, which is like an API for using Jupyter notebooks for doing super easy like PCA and structure and RAXML. There's all kinds of different tools where we've taken all the complexity of managing replicating runs and managing files and all this, and we just do all this housekeeping for you, so you can just have a Jupyter notebook where you can analyze and plot results from your data, which is super helpful for reproducibility, right? Like then you can publish the notebooks with your manuscripts and put the notebooks on your GitHub, so that all your analysis for all your manuscripts can be replicated super easily. So I think that that's one of the kind of like primary strengths of IPyRAD, is the analysis tools.
Yeah, Jon.
Yeah, I would agree. I certainly think that IPyRAD has the best documentation of all of the tools, and I've always liked the way that IPyRAD has encouraged the iterative approach to analysis, where you are trying to evaluate at every step what you're doing. I think that's really important, and something that I always like. So I also think that docent and PyRAD/IPyRAD kind of came about in the same sort of need, is that we had data sets that were perhaps not working the way we thought were working when we were analyzing them with existing software packages at the time. And so both of the packages like highlighted being able to handle indels in your reads for clustering, and I think that made a huge difference. And I think Melanie's paper showed that a lot too. And now a lot, I think, like kind of what Isaac said, the pipelines have really kind of caught up with each other in different ways. So there isn't a huge amount of difference between the two, or between the three, I'm sorry. And, you know, I think my goal with Docent was to, and the whole reason it's called Docent is that I tried to take tools that were made for every specific step in this type of analysis and write a script that basically like allowed you to use what I thought were the best tools at the time to get the job done. And so the pipeline was meant to be a guide, and that's why I called it Docent and just added the extra D, because originally it was only for DD-RAD data, but now it can handle pretty much any kind of RAD data you throw at it. And yeah, I mean, I've tried to make Docent as accurate as possible, and that's kind of the place where I like to hang my hat, is that especially for de novo assembly and genotyping, that Docent will do the job as best as anything else, and generally it's pretty fast. That we certainly, people find ways to break it all the time. I don't, you know, it happens. You throw enough reads and not enough memory at something, and it will crash. And so and I, you know, I think both the like PyRAD, iPyRAD pipeline and Docent like embrace the open coding that was part of it. Like all of our source code has been open from day one, and I think that makes a huge difference, because it's meant to be customizable. It's meant to be accessible, and you know, with the help of, you know, other people moving past that. And I think that was something that wasn't present at the time, when, at least when I developed Docent, when PyRAD was being developed, which was just about the exact same time. You know, I think it's important to have it in that kind of open framework. And so to me, those are kind of the highlights that I like to hang my hat on about Docent.
Yeah, so we did actually have another panelist who had a lot of experience with stacks and testing stack parameters, and at the last minute she couldn't come. So we're not just preferentially highlighting these two. But yeah, so Melanie, if you want to maybe talk a little bit about your paper and its results.
Sure, and I can mention stacks too. So we ran a simulated, or we did a simulation paper where we looked just at the de novo assembly step of a few different pipelines, and also looked just directly at the product from the de novo assembly. So we simulated data, put it into the de novo assemblers, and so we knew exactly what we expected to come out of that step, where it basically should just take that simulated data and either replicate it exactly if there's no mutations in the data, right? If you give it a bunch of unique sequences, it should just spit those back out to you. But then we introduced SNPs or indels at varying mutation rates to see how that affected de novo assembly. And then we varied a couple of parameters also to see what that did. And so we found that CD hit was the best performing de novo assembler, which is one of the assemblers that's an option in Docent. And I'll just say that CD hit, stacks and stacks 2, which perform differently, and I can talk about that, and vSearch performed much better than other assemblers that were designed for whole genome sequencing. So, or sorry, for whole genome assembly. So Velvet, for example, is a very popular whole genome assembler, but we found that it performed very poorly with this RAD data. And it seems that it was trying to assemble these sequences that are never meant to overlap with each other into more continuous assemblies. And so that was important, because Velvet is being used by people for short read data. And so these pipelines that we're talking about, iPyRAD and Docent and stacks, you know, were designed more for this RAD data. And so I think that's something to think about when you're trying to choose your de novo assembler, or, you know, the whole pipeline that you're using. And one thing I'll note about stacks is that generally, yeah, it performed very well. It did run into some issues with insertions and deletions. And so we do talk about that in our paper, where insertions and deletions often meant that sequences were split into more context than they should have been. And stacks had the hardest time dealing with that issue. But otherwise, stacks performed very well, and there are downstream filtering steps that you can take to try to deal with that, to try to remove some of those kind of false loci. Again, we can talk about that more, but I think, like both Jon and Isaac said, that, you know, all these pipelines are making moves forward and are doing pretty good, but we just have to be thinking about how we're using them and what parameters we're setting in each of them.
Yeah, and so John Swenson in the chat has a question that I also had. When stacks struggled with indels, was that stacks 1 or stacks 2 or both? Because I know they've said that they now allow for indels.
Yeah, good question. So when we first did our project, stacks 2 had not been released yet. So we proceeded with stacks, and then stacks 2 was released. And one of the major improvements was to deal with indels. So we found that stacks 1, the original stacks, had an issue, yeah, over splitting or under assembling. These terms are terrible, but that depends on which one what you want to use. So loci that should have been a single config in your assembly were split into multiple configs. Stacks 2 dealt with that better. It was more likely to put those loci or those sequences together into a loci correctly, but stacks 2 had some issues producing untrue genome fragments. So we measured assembler performance by looking at the number of configs that were produced in the de novo assembler compared to how many we expected. But we also looked at just, are those real genome fragments? And some of the lower performing assemblers dropped out of kind of the running based on that. And to be honest, we're not totally sure what is going on that's making that happen. I think some more simulation work needs to be happening to figure that out. But stacks 2 was closer to the right number of configs, so that was an improvement, but was starting to produce some non-true sequences. So I'm not sure what that means.
Awesome. Yeah, John, were you gonna say something?
Yeah, I'll add that in my own like testing when I'm doing horse race competitions and checking stuff out, I found the same pattern that stacks 2 or stacks 1, whether you enabled the gapped algorithm or not, because that was an option in later versions of stacks, like stacks 1.4 and on, you could do the gapped algorithm, then it became default, I believe in stacks 2. The gapped algorithm helps, and it does get closer, but it does not seem to fix all of the issues. I found the exact same thing that Melanie did in her data sets, that it gets closer, but it's still not quite. And it's worse the higher level indel polymorphism you have. That was what I found as well. So
Great. So maybe we'll do about 7 more minutes of questions from us and then open it up. And so something that you've all, I think, touched on a little bit is the importance of optimizing these parameters in order to make sure that what you're getting is the most accurate result, basically. And so, we've talked a little bit about the importance of doing that iteratively, checking your data at each step. If you could maybe talk a little bit about what parameters in the pipeline you usually use, have you found make the biggest difference in accuracy, and how you test those parameters?